Hello, everyone, and thank you for joining us today. My name is Jay Singh, and I will be your host for this NASA Technology Transfer Program webinar on NASA Ames high-temperature materials. Our presenter today is Jay Feldman, and he will be speaking about his three-dimensional multifunctional ablative thermal protection system, also known as 3D MAT. Following Jay's presentation on his technology, I will be given a short presentation on how to license NASA technology. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them in the chat box and we will answer them during the Q&A session at the end. So at this point, I'm going to turn it over to Jay. It's all yours.
Oh, thank you, Jay, for turning it over and the introduction. Appreciate it. Thanks, everyone, for joining today. I'm happy to tell you about the technology I helped develop. Called 3D Multifunctional Ablative Thermal Protection System. My goal today is to just give you a bit of a story on the background of the material, this unique composite material, why we needed to development, how it's being used, and some of the properties of that material system. I will mention up front, because I didn't put it anywhere in the presentation, that this composite material system, because of its use on an ablative heat shield, it is ITAR restricted, so if entities are interested in a technology transfer of this technology, those companies would need to be ITAR compliant. Okay, let's see if I can advance to the next slide. There we go. So why did we need to develop this 3D ablative composite material? It comes down to the Orion multi-purpose crew vehicle and the development of that. So far, Orion has flown one time, a flight test in 2014. This was a orbit around the Earth and back in, landing in the ocean outside of San Diego, a recovery shown on the top right here. The Orion multipurpose crew vehicle is going to transport astronauts to the Lunar Gateway for access to the moon and eventually deeper into the solar system. I should point out that Artemis 1 is the next mission to fly, and that's going to happen later this year, a few months or so from now. And then astronauts will start flying missions in a few years, targeted for 2023 and beyond. So 3D MAT is one of the technologies we specifically developed for this Orion mission to enable part of the heat shield design. Okay, so what is the compression pad? That's the material that we developed. 3D MAT is for the compression pad function of the space vehicle. On the top right here, you see a photograph of the Orion EFT-1 vehicle being prepared for flight. The heat shield is this bottom part with a reflective material covering it. You can see some holes in the heat shield, and those holes are the locations for the compression pads. If you look over here on the left, the crew module, which carries the crew, and that's the spacecraft itself, that is connected to the service module. They are physically connected through the heat shield of the Orion crew module on the rocket stack up, and so that's all structurally integrated as part of the launch. And so what we actually have here is a heat shield, which you normally want to be a low density material. You don't want to add much weight for launching into space. You have a heat shield that's low density, but these regions where it's structurally connected to the rest of the rocket, you need to have a very robust structural ablative material system. And that's where 3D MAT came in, because we couldn't find a material to meet the requirements of that particular location. I'll touch on the requirements more specifically in a little while, but as you can imagine, in that role as a compression pad, this material has to withstand launch and ascent structural loads. There's a pyroshock event. You can see the material that 3D MAT replaced is 2D carbon phenolic, a laminate material that's shown here. This is the actual compression pad from the first launch EFT-1 vehicle. There's an explosive bolt here, and that's how the crew module and service module separate ahead of the crew module re-entering the Earth's atmosphere and completing its mission. So this service module separates for that phase. So that's kind of the overview of the component that we need to target. So what was the problem with the compression pad for that design? So the initial design is kind of shown in the top left here, and it was an all-composite design, simply with a hole in the middle for that explosive bolt to feed through and do its role. The problem was that this material was a laminate, a 2D carbon phenolic laminate material, and it had, as laminates do, they have poor interlaminar strength. So that Z direction, it's just held together with glue. There's no fibers in the Z direction. You can get some poor strength. So this design didn't work out. And so for the Earth Earth orbit only design, that first flight test, what was developed here was a metallic steel insert in the compression pad to help carry those structural loads. But that's a kind of a problem because we're trying to manage the thermal conductance into the heat shield, into the vehicle. We don't want to cook the cargo or crew. Metal's a thermal short. That's not something that we wanted to have in there. So we wanted to enable a better design for the compression pad, and thus we looked to developing a 3D composite that could meet all of the structural requirements as well as the ablative and thermal requirements for this component. I should point out, as is down here in this third billet, while the first mission just orbited the Earth, all the future missions will go to the lunar region and back, traveling at a higher velocity, entering the Earth's atmosphere at a higher velocity, and creating a lot more heating. So again, that metallic insert creating a thermal short could be problematic in that scenario. So we wanted to enable a design that wouldn't need that. All right, a little bit more on the specific requirements here. As you can imagine, there are thermal and structural requirements for the compression pad. A few highlights here. So thermally, we design the compression pad and all of the heat shield to reach a maximum of 500 degrees Fahrenheit at the bond line, and that's where the compression pad is actually bonded to the structure of the vehicle. So that temperature can never exceed 500 degrees Fahrenheit at that interface. And then there's a variety of structural loads, compression, moment, and shear loads. This composite also has to maintain a significant preload through that tension tie or explosive bolt. There's that pyroshock event I mentioned, an explosion in the bolt happening just right next to the compression pad. And then finally, one of the driving requirements for developing this material was actually the size. The pad material needed to be at least 3 inches thick by 11 inches in diameter. So it's a pretty significant size for a 3D fully dense composite. Just a note on some of the challenges, we'll get into more details later, but there was an aggressive schedule to develop this system in time for the Orion preliminary design review. We had only 3 years to go from drawing board to technology readiness level 5 or 6 at PDR. That's a very aggressive schedule for a new material development. And along the way, we had to develop new weaving and resin infusion processes to enable us to meet this size requirement. So scaling up was a challenge, and we did multiple process refinements along the way. I'll touch on some of those. So just to give a quick overview to make sure we're all on the same page, what are we talking about in terms of this manufacturing process? One can procure quartz yarn commercially from Saint-Gobain, and then undergo a 3D weaving process. That's kind of one of the magic steps here. Create a 3D woven preform. There's a ruler down here for scale that roughly 12 inches by 12 inches by 3 inches thick. And then after that's woven, there's a secondary resin infusion process to create a fully densified 3D composite billet. And then that gets final machined into the component, in this case, a compression pad. All right, so weaving scale-up was really a big challenge for us, and we believe this to be the first ever achievement of a continuously woven, automated jacquard loom weave of this type at this scale. So 12 inches by 3 inches is the weaving cross-section. That would be this part down here as it comes out of the loom. The loom is way back here. This is the loom harness, which NASA funded. Our weaving partner for this is Bally Ribbon Mills in Pennsylvania. So they have all the hardware residing there still and produce these parts for Orion now. We have a 57% fiber volume fraction, so that's close to the theoretical maximum, packing as much fiber in there to give us the most strength and structural robustness we can achieve. We have roughly a third of the fibers in each of the X, Y, and Z directions to try to give us somewhat symmetric properties in the material. And state of the art was a cross section of weaving that was about a factor of 4 less than what we ultimately achieved. So that was the big challenge in terms of weaving. I have a video of the manufacturing. I think I have 2 videos to show. I'm gonna try to come back to those at the end. I think it'll be easier to switch to the 2 videos at the same time. So suffice it to say, I'll just introduce the video now, and we'll talk about it a little bit more later. But this is a kind of a zoom in of the weaving process. The harness is shown here. There's well over 1,000 individually controlled yarns. Those feed in from the creel shown in the back here. There's not a really good scale in this picture. I apologize for that. This is, like I said, about 12 inches wide. So the X warp and the Z fibers feed in from the back here, and then you'll see in the video there's a shuttle going back and forth that fills in the, well, they're called fill fibers or the Y direction fibers, and we'll show that at the end. In terms of resin infusion, this was also a significant challenge, a little bit surprising to us how challenging this was. We were required to achieve less than 2% porosity throughout the entire volume of the billet, which is again is 3 by 12 by 12 inches. That's a significant requirement. While resin transfer molding is regularly used for thin composites, less than 1/4 inch thick, say, something on the order of the volume we're achieving here, it's much more challenging, not well established, not established at all, and to be able to eliminate the porosity throughout was definitely a significant challenge for us. We had really 5 failed attempts with different approaches, different facilities that we worked with, and ultimately developed a process with San Diego Composites to do this cyanide ester resin transfer molding process that's a little bit unique to our material system. All right. Just a little bit on some of the properties here. This is a compression pad, so the compression strength is highly relevant. This is a stress strain curve shown here, and the black, red, and green lines show the on-axis data compression stress strain curves for 3D mat. And so we're receiving failures up here in the 60,000 to 80,000 pounds per square inch regime. That's quite high. That's good. For comparison, the 2D carbon phenolic material it replaces on-axis strength was about 50,000 pounds per square inch. So we've significantly gone above that. I'll point out that when you go to the 45-degree bias XY compression test, we do see yield at a much lower strength, down here about 25,000 pounds per square inch, but there's a good bit of yield before an ultimate failure way up here at 60 KSI, and through some hysteresis testing, repetitive cycles and compression testing, we were able to show that you can go through this yield point and back down many times without compromising the ultimate strength of the material at or above 50,000 pounds per square inch. So it's a very robust material system. Okay, just a brief summary of some of the other testing we did is shown on this chart. Some of the material properties are shown here, and they're shown as a relative to the 2D carbon phenolic material that this replaces. I already touched on the compression strength, which is significantly above the carbon phenolic material. Really, where this material shines and where it needed to shine is in the interlayer, the Z strength, what would be interlaminar for a 2D material, interlayer for this material. We're a factor of 9, the strength of the 2D carbon phenolic. That's where what we really needed to improve in this is have a high strength in all 3 directions. So that's great. I'll point out that we also improved upon the thermal conductivity. We want that to be low. We're, again, trying to keep the heat out of the vehicle. Our thermal conductivity is about 3/4 that of the carbon-based system, the 2D carbon phenolic. So this is all really great news for us. We did a whole host of other testing. A few articles are shown here from stress relaxation and shear, some pyroshock simulation along the way. but a full suite of material properties and structural testing has been performed on this material system. I want to touch on arc jet testing. That's extremely important for our application. Arc jets, I'm not going to walk through all the details of this, but the arc jets are an incredible ground test facility that are able to come close to simulating on the ground environment that's relevant for Earth or other planet entry. So supersonic flow, extremely high temperatures and heat fluxes, relevant pressures and shears. So we use this facility to qualify these materials for flight. This facility is here at NASA Ames Research Center. This chart summarizes some of the initial testing we did with 3D Matte. We've actually done a lot more beyond this, but this was the initial work done in these first 3 years. We tested in the 20 megawatt facility at NASA Ames, heat fluxes up to 660 watts per square centimeter. For folks that may not know, I can use the space shuttle as a reference. That achieved the highest of 60 watts per square centimeter, a factor of 10 lower than what we're looking at for this mission. And that was achieved on the wing leading edge. We tested at relevant pressures, durations of up to 200 seconds, and then our maximum surface temperatures were anywhere from 1500 to 2400 degrees Celsius. And again, that's at the very surface here, the left side of the article, just a couple of inches underneath that, we're down at about 200 degrees Celsius. So very, very significant temperature gradient across this material. Again, I'll show a video towards the end of the session today. But before we get there, I want to show a few results from the arc jet testing. The articles are shown on the left here. These are 4 inches in diameter. This is a pre-test photo and a post-test photo after it's been pyrolyzed and charred, somewhat ablated and receded in that test. You can cross-section these post-test articles, cut them in half, and you can see the char layer that's developed towards the top. You can also see in this picture, I hope, there's a 1/2 inch diameter instrumentation plug in these. And in that plug, we have thermocouples embedded at various depths, so we can characterize the temperature as a function of time and depth in the material as we do an arc jet test. And that's very important, so we want to make sure we can simulate accurately what we expect the temperature profile to look like in the actual mission. And so on the top right here, I'm showing a plot that has the actual test thermocouple data shown in red, and then the physics-based model that computes what we predict that temperature profile will be for this specific arc jet test. That prediction is shown in black, and that's a pretty good approximation of what was actually observed, a pretty good prediction for a physics-based model and a rather challenging material to model. All right, with that, I think just a few more charts on the material itself. Arc jet testing of the 3D Matte revealed no failures, and that is in contrast with the 2D carbon phenolic material. These are side views of the articles. After arc jet testing 2D carbon phenolic, you sometimes see cracks develop between the lamina. That's not a surprise, but it is a potential problem. We predicted that this would occur in flight, and that very first flight test used carbon phenolic. And we did, this is a flight hardware, this is an actual post-mission photograph of the compression pad on Orion. It's just carbon phenolic. This is the middle here is the explosive bolt, which is separated from the crew module from the service modules, rusted out because this landed in the ocean. And then we see these cracks in the carbon phenolic, which again, we expected would happen in the first mission and was something we wanted to avoid in future missions, and thus the development of 3D Matte material. So in summary, I'll just say that 3D Matte is a structural ablative material. It's qualified for the Orion multipurpose crew vehicle. This material composite combines high strength, low thermal conductivity, high temperature capability, and thus is a unique high performance composite. The Artemis 1 flight test scheduled for November will be the first flight of this material in space. Some of the flight hardware is shown down here below. It's actually, although it was developed specifically for the compression pad, Orion really liked the properties and performance of this material, and they have used it in 18 different locations of Orion's aeroshell. So the compression pad on the heat shield, and then many other locations on the back shell where there's some structural requirements, such as this article shown here. This is about 20 inches long. It's made up of multiple pieces of 3D mat, and this is the umbilical interface plate for feeding in, electrical and other life support from the service module to the crew module. So with that, I will attempt to switch over to a couple of videos, if I'm able to do that. Okay, here we go. Don't know that we need the volume on this. So this is the loom in action. I mentioned you see the shuttle going back and forth here that contains the fill yarn. It has to go back and forth for each one of the layers in this material. In the Z direction, it's built up about 50 layers, and the Z direction has to go through each one of those 50 layers before the loom can advance one step in the X or warp direction. So it's a very slow process to weave this. A 13-inch long part takes on the order of a day of continuous weaving. And I have one more video I'll show that may be of interest. This is an arc-jet test. And let's see if I can, also don't need the volume there. You're seeing a close to a side view of the arc-jet article I showed earlier. So this is 4 inches in diameter and a little bit of an oblique side view. And it's this is 660 watts per square centimeter, so it's extremely hot, very high heat flux in there. And what you'll start to see in a minute is that there's actually a little bit of melt flow. You can start to see these little waves developing on the edges of the coupon where there's some shear forces. So we're actually melting those quartz fibers just a little bit, so we know we're over 1700 degrees Celsius at that point. In order to achieve that, our instruments tell us we're closer to 2100 degrees Celsius there. In the center, you start to see a bright spot, and that's the instrumentation plug. We're actually slowly ablating through this material a couple of millimeters to reveal the underlying instrumentation of the article. So that's what I wanted to share with you today, and I would be happy to take questions if Jay has any of those, Jay Singh has any of those for me via the chat. And thanks, folks, for your attention today.